had my bachelor's in University for Development Studies in Ghana. And then, of course, currently I'm working here as an assistant professor at Cal State Fullerton. And currently I'm also associate editor for the CDC Preventing Chronic Disease. So, and then I have several research collaborators, and most of which are the NIH and then also Tennessee Cancer Registry. So now let us start with why. So my question will always be, how did we get here? And that's a big question which actually needs kind of a big answer. And the reason why we are here is always our search for the unknown as human beings. Because so many things going on within our population in terms of health, in terms of economics, in terms of finance, in terms of, different interdisciplinary field and different attributes, characteristics that is actually happening within our population. But what we don't know is how are we able to discover so many of the different things which is happening within our population, which sometimes causes chaos within our population, if it is health issues, if it is economic issue, economic crisis, maybe. So our search for the unknown is what have actually driven us to this far when it comes to data inference, where we have the entire population, and then it's hard for us to be able to predict things using the entire population. But however, what become truly and available to us is some sample within the population, which of course we have access to, and based on which we are able to use this sample data we have within the population to be able to at least try to predict the true state of nature within our population. So if it is health-wise, if we would want to, if it is, let's say, disease outbreak, we would want to discover perhaps the cause of the disease outbreak based on a sample, right? So practically, when we talk about data inference, we are actually looking at how we are able to draw conclusion about the entire population based on the sample we had. And that's how it have actually even make data analysis more important and data inference more important, because if you wrongly predict what is happening within our population, then there is chaos. Because think about it this way, let's say not long ago there was COVID-19, right? And industries were coming up with vaccines. So assuming in that industry that came up with the vaccine, by prediction, the prediction that was made was that the vaccine was good, but indeed the vaccine wasn't good, but the vaccine eventually was administered to people. What then happened? We may be feeding people system with maybe wrong vaccine, which can cause problems. But on the other hand, too, if the vaccine is good, and then we end up predicting that the vaccine is not good, what then happens? We are collapsing people, companies, right? Which is a huge thing. So that's how it makes data inference very important, and the careful analysis of it is really very important in allowing us to understand and know truly what is happening within our population. So when it comes to statistical inference, basically we look at two major things here, which is the estimation and then the hypothesis testing. Now, the hypothesis testing is, if you think about a claim, right? You just make a claim within the population, and then you would want to test to ensure to see whether the claim that have been made is correct or wrong, right? And then that happens through the use of data set. And through the use of the data set, that's where the estimation comes in here. So we would want to use a sample, a subsample of the population to be able to estimate, which we do call the point estimate, to be able to make sure this point estimate is as close to the true state of nature within our population. So in other words, if we are to, let's say, predict the mean age of United States population, right? But we are taking a sample because US perhaps maybe have close to maybe 400 million people. So we are just taking, let's say, a subsample of 1 million, but we would want to be sure that this sample is able to draw us as close as possible to the mean age, assuming we are to use the entire US population in calculating the mean age of the people. And so that's how important is it. And then, of course, we have the confidence interval, which with the hope that if we have the population parameter, the population value is able to fall within the interval. And then we said we are going to have what is called the null hypothesis, and we are going to have what is called the alternate hypothesis. And then our assumption about the population always we start with the null hypothesis. So in this workshop, I wouldn't go so much into discussing this hypothesis and stuff. And what we are going to do is we are going to be able to use R in performing certain analysis to be able to make certain conclusions, assuming we have a data set, and then you'll be able to, by yourself, apply on your own. So the aim of this workshop, we are going to have two parts of the workshop. Part one, we are going to be able to using R or R Studio to perform t-tests, to perform ANOVA, specifically one-way ANOVA, to perform a chi-square test. And then part two, we are going to also be able to use R for correlation and then also regression analysis modeling. So again, this is able to just give you some form of fundamental or basics in R when it comes to inferencing and modeling. Okay, so if you haven't installed R yet, if you go to the website, you are able to install your R, and then also it will guide you to install R, and then also the data used in the website used for this workshop can also be found on the website, so you can easily go there and then download those information. Excuse me. So now let us look at part one. So what I'm going to do is I'm going to just run you through some R codes and how those analyses were performed, and then the outputs or the results of those analyses and how you are able to make sense out of those analyses or specific information in which you'll be able to pick from there. And then after part one, maybe we give ourselves about 5 minutes break, and then we start with part two, which is going to be the correlation and then the modeling part. So, and then once I run you through all of them, I'll now jump into the R Studio itself and then use it to practically perform the analysis for you to see how you can actually do those analysis in R Studio in case you would want to. But again, all those guides are also available on the slides I'm going to show you. So first of all, you are going to read our data into R Studio or R. Specifically, I'm using R Studio, but if you are using R, it's pretty much the same thing. You can actually perform the analysis. The difference between R and R Studio is just like having your car, and then R Studio is just like a decoration of the car, right? So R is the engine itself, and you have the R Studio, which is making the car very decorative, right? And that's how it is. So you always have to install R first before you install your R Studio. Okay, so you load the data set, and then once you have loaded the data set, which we are going to use, the data file we are using is a CSV file. So we are going to, you load it by calling this function, which is, we are going to name our the data frame, which is DF, and then we are going to use this, which is read CSV choose, to be able to, and this one actually take you to the location on your computer to be able to choose the data into R or R Studio. And then also you can name your, you can look at the names of the columns of each of the data you have, or maybe the variables within the data. You can perform some summary statistics just to be able to know the behavior of the data set you have based on the variables. And then you have the end row and then end call. So So there's the function. So n row into bracket the data frame, which is this was what we assigned to our data, which is the DF, and that gives it the number of observation or maybe the length of the data set. And then you have the n call, which is the number of columns we have in the data. And if you are performing, let's say, if you're into data science or machine learning, usually they call it the features or maybe the attributes within the data set. Then also, we are also going to remove certain things out of the data, which would include missing values or unwanted information out of our data. And the data we are using here is going to be the hints data. Okay, so now let us look at, we will be starting to perform analysis on t-test, which in other is called the student t-test. So the t-test actually test the significance between the means, test the significance between the means of two groups, or it can even be one group whilst taking their variance or distribution into account. So before you perform t-test, usually you look at the distribution, the randomness of the data set, and then the variance of the data set. So we said the distribution the data have to be continuous, the data have to be randomly, you have to randomly sample from the population, and then you have the homogeneity of the variance, which means there should be some variability within the data set. And then also you have the data have to be normally distributed. Now, when you talk about data have to be normally distributed, more often, if you have a very large sample data set, we are not really worried about the normal distribution of the data. And someone will ask, how large should my data be? And usually the threshold they give is if you have a data set of more than 30 observations, it could be considered as a large enough data set. But I think the larger your data set, the better, and the closer your sample estimate will be approaching the population parameter. So always, if you have a very large data set, the better. So there's the R command or the R function for t-test, which is t.test. And then you have all this command, which is, so I'll be showing you how you can actually read on all these commands in R by just using the question mark t-test. And that actually gives you the meaning of all the information. So we have the alternate. The alternate is telling you the type of test which is being performed, which is the two-sided test, left-sided test, right-sided test, which is less than or greater than. And if it's your test a paired sample, and by default R give the null hypothesis to be 0 by default, but it can be actually changed. And then also remember we spoke about the homogeneity of the variance. So if there equal variance or there is no equal variance, it has to be satisfied. Again, if you have a very large sample, usually by default, we leave it as the variance there is equal variance or the variability in the data set. But if you have a very small sample, that's when you have to be very specific to ensure that you minimize any error. Okay, so once you have actually performed your t-test, for instance, so you have your continuous data, and then we have already called our data set, which is the DF. And so within our data, we are going to perform a test to know the mean BMI level. And by default, the null hypothesis is equals to 0. So in other words, we are setting our null hypothesis that the mean BMI is equals to 0. And then we are performing the test to see whether the BMI is not equals to 0, which become our alternate hypothesis. So once you have performed that test, this is going to be your output. And then what you are going to see, most of the important statistics you look out for in your output is going to be your p-value. And then, of course, you have your confidence interval, and then you have the mean of that particular variable, which is BMI. So in this case, we have the p-value. We set our level of significance to be less than 0.05. So we have a p-value of less than 0.05. is statistically significant. So given this p-value, we said is statistical significance. Hence, and whenever your p-value is statistically significant, you reject the null hypothesis. And when we reject the null hypothesis, what we are concluding is that the population, the mean BMI is not equals to 0 by default or by. But of course, R also allow you to be able to set your own mean. So assuming we know within the population that the mean BMI is the population mean for BMI is 20. So R can let you set it, and then now based on your sample, you are able to say, are you going to get an estimator which is going to be equals to the population parameter, which is the mean BMI, to be equals to 20. And then again, within the t.test, you are able to set your whether you are performing a right tail test or left tail test. By default, R perform two-sided test, but you can change, you can use the alternate to change it to, let's say, for instance, less than, to be able to perform a left-sided test. Then also, we have also, you can also specify your confidence interval. By default, we are giving 95% confidence interval, but you can specify your confidence interval to be, let's say, 90%, and then you'll be able to come up with your test. Okay, so moving away, and that's a one sample test. But the next thing is, so one sample test is you just have a one sample. So in this case, we're looking at only BMI. But now, what about if we have a two sample test? Let's say what we call the independent sample t-test. So in that case, you are looking at having a continuous variable. Let's say we still have our BMI, and then we have gender, male and female. So we would want to know, is the BMI level of male and female equal? And that will become our null hypothesis. So the null hypothesis that we are setting the population parameter to be equals to, we are saying that the mean BMI of male and female are equal. But then we now, based on our sample, we are now coming to perform the test to be able to see whether we are going to reject the null hypothesis or we are going to fail to reject the null hypothesis. And if our null hypothesis says the mean BMI is equals to of male and female are equal, then alternate hypothesis by default is not equal, which is a two-sided hypothesis. So now once we have used the t.test, again, df is our data, and then within our data, we are calling BMI, which is the variable we would want to test. And then we would want to test it on male and female. So we have gender within our data set, which we make a factor of 8, so that R is able to recognize that they are categorical variable. And then we then perform that test. And then also, again, if you, given the assumption of t-test, where we said it has to be normally distributed, homogeneity of the variance, or there has to be randomness within the data, or data, there should be some variability within the data. If you can still specify your equal variance. Is the equal variance true or not? That's if you know, you can specify. If you don't know, you may choose not. But again, if you have a large sample size, usually that aspect could be ignored. Then again, once you have performed this independent t-test, again, with independent t-test, you have one continuous variable, and then you have a binary categorical or nominal variable. So in this case, we have gender, which is male and female, and then we are looking at, is the BMI level of male and female the same within our population? And then again, this is the p-value. So the p-value says, the p-value is 0.977, which is a high p-value, which is greater than, if we take a level of significance of this is 0.05, this is greater than 0.05. So we fail to reject the null hypothesis. So if we fail to reject the null hypothesis, then we are concluding on the null hypothesis that the mean BMI of male and female could indeed be equal within our population. And then we have the confidence interval. Again, within the confidence interval, if the confidence interval includes 0, then we say that we are failing to reject the null hypothesis. So we can actually use the confidence interval to make a conclusion, whereas we can also use the p-value to also make a conclusion. And in either way, it's going to actually give you the correct conclusion. And then we can have the mean BMI for male and female, which is group 1, I guess, is the male, group 2 is the female, and then we are able to know this. And this one is actually the sample mean of male and female. Okay, so we also have another aspect of it, which we call the paired sample t-test. So the paired sample t-test, the way when you think about paired sample t-test become, let's say, before and after kind of assessment, right? Let's say you apply some intervention. Before you apply the intervention, you measured the individual. And then after applying the intervention, you measure the individual, and then you want to test and see the differences between before and after maybe the intervention was given. So in this case, you need 2 continuous variables to be able to, and then they should have the same sample size, right? So we are going to select data from our BMI score, so let's say 6 individuals, and then we are going to have a BMI score of score 1, which is given. So we use C to actually assign by using the, we are assigning score 1. And with this C, you are actually developing a vector. Okay, so you are actually assigning a C into a given vector. And then also you have score 2, which is also this. So we have, each of them have a sample size of 6. So we are going to perform, it's a score. And then the first score is people who actually BMI level were measured, or their BMI level was measured before they participated in a physical activity. So we would want to know that the BMI level before the individual actually participated in a physical activity, is it actually the same? And then after they have performed, they have participated in the physical activity, are they the same? And our hope would have been that after performing a physical activity or participating in a physical program, we anticipate that your BMI level fall, and maybe perhaps we achieve some significant difference between the two, but we don't know whether it is the truth unless we actually test. So we set a null hypothesis of, so this, and that gives us a pair sample t-test. So we set a null hypothesis of score 1 to be equals to score 2, which is again within our population parameter. We are assuming that the null hypothesis of the mean score of BMI 1 is equal to the mean score of BMI 2. That's before physical activity and after physical activity. And there's actually, if you perform such a test, there is going to be your results. And then again, in the results, you're actually going to see the p-value. And if the p-value, which is greater than 0.05, we fail to reject the null hypothesis. So by failing to reject the null hypothesis, again, we are saying that the mean BMI before physical activity is almost the same as the mean BMI after the physical activity. And then again, you have the confidence interval, and then you have the mean difference. So the mean difference is, it is calculating the differences between these 2 scores. So it is score 1, score 2, the difference. So score 1, so score 1 value, the first value of score 1 and the second value of score 1, the first value of score 1 and the first value of score 2 is representing one individual. So the first value of score 1 is the individual's BMI score before they participated in the physical activity. And then the first value of score 2 is the mean BMI of the individual after the physical activity. So what R is doing is R is taking the differences and then finding the mean. So the mean difference of BMI of score 1 and score 2 is given by 2.0667. Okay. So now let us move a step further. So we actually perform, looking at the, we perform an independent t-test, right? Where we have 2 variable. One is a continuous variable and one is a categorical variable. But the categorical variable is a binary variable, right? So that allows us to be able to perform kind of the t-test, independent t-test. But what if we still want to perform a t-test for a single continuous variable, but that continuous variable have more than 2 levels? So let's say that continuous variable have 3 or more levels, right? And that actually sends us to a step further of performing what is called the ANOVA. And specifically in this particular workshop, we are actually going to look at the one-way ANOVA. Maybe in future workshop, we can consider a deep into the other type of ANOVA. So with one-way ANOVA, we are actually looking at, of course, a continuous variable, and then we have which could be the dependent variable, and then we have the categorical variable, which should have more than 2 levels. So, and then we set the hypothesis that given the levels of all the categorical variables, the mean of the dependent variable is the same for each of the levels of all the categorical variables within our population. So let's say, assuming we take age, the level of age, right? We can have so many different levels of age, let's say less than high school graduate, some college degree, a college degree, master's, PhD. So the question now becomes, if we take the BMI score, is it the mean BMI, is it the same for each of these levels of education? So given that we have more than 2 levels of education, hence it allows us to use ANOVA to be able to actually perform that. And this, again, there's a command or function for ANOVA, and then these are the arguments within it. So again, if you use the square root of AOV, that actually, or the help of AOV, inverted comma, that actually give you more information about ANOVA. Okay, so now let's assume we perform our ANOVA, right? So we have been able to perform our ANOVA test. We are now coming to test the BMI across 4 levels of education, right? So now we set our, we assign our function, which is the ANOVA function, to some name, which we call it BMI ANOVA, right? And then we call our data, and then our data we are calling within the data, which is DF, our data frame is DF. We are calling the $, always allow us to be able to call that particular variable out of our data set. And then we are now looking at it at the different levels of education. Again, we have factor in a parenthesis, DF, again, DF education, meaning within our data, we are selecting education. And then the factor allows us to make our thing that variable is a categorical variable. Okay, so now, once we have done that, we now find a summary of this model we developed, which is the BMI ANOVA, which is the ANOVA model. And that summary is going to print out the results for us. And so this is actually the results we have here. And then we can also print out only the means for each of the levels of education, that the BMI means for each of the levels of education. So once you have performed your ANOVA and then you have printed out the results using the summary of the model, the ANOVA model, this is what you are going to see. And of course, this is what is going to be your p-value. So you are going to have the p-value here. And again, when the p-value is less than 0.05, statistically it's significant. And so what then it means is that we reject the null hypothesis. And what is the null hypothesis? The null hypothesis was that the mean BMI level for each of the level of education are equal. But now we are rejecting the null hypothesis, which means in the nutshell, what we are saying is that no. If you take the BMI level of each individual, given their educational level, their BMI level is not the same, right? And then also we have, this is the grand mean, which is the total BMI for all the level of education combined. And then for each of the level of education, their BMI level. So if you look at level of education 1, education 2, education 3, education 4, this is their mean BMI level. And this is the number of data set or information we have for each of those groups. So we have observation of 136, 383, and then in that order for the different levels of education. Okay, so now we can even take a step further that, wait a minute, assuming the mean BMI level, given our model, the ANOVA model is telling us that the mean BMI level is different for the levels of education. But is it the same difference, assuming we have to pair each of the levels of education? So let's say we pair level of education 1 with level of education 2. Is the mean BMI different? Level of education 3 to level of education 1. Is the BMI level different? Level of education 4 to level of education 1. Is the mean BMI level different? And we do that using the Tukey HSD of our ANOVA model, and that gives us a pairwise comparison. So with that gives us this output, and then this is the comparison we are going to do. So we have 2, 1, which means education level 2 versus 1, education level 3 versus 1, level 4 versus 1, level 3 versus 2, level 4 versus 2, level 4 versus 3. And for each of them, we are now going to have their p-value given to us, right? And then, of course, and then also we are going to have their 95% confidence interval by default also given to us. And so if you have the confidence interval including has 0 in 8, then again, it's not statistically significant. And then, of course, you should have a similar conclusion when you have the p-value, which is a very large p-value. So for instance, if we take level of education 2 versus level of education 1, and we ask the question, are their mean BMI level the same? The answer is we fail to reject the null hypothesis. So which means, yes, possibly the mean BMI level of education 1 and 2 are similar or the same. Level of education 3 and 1, also the p-value is very high, which is greater than 0.05. So again, with this, we can say that level of education 3 and 1, their mean BMI level is the same. But if we go down, if we take level of education 4 and 1, and then 4 and 2 and 4 and 3, we can see the mean BMI level. We are going to reject the null hypothesis because the p-value is less than 0.05, right? So which means that if you take this level of education if you pair any of the level of education with level of education 4, then the mean BMI level is what is different. And that's how we actually assess the pairwise comparison using the ANOVA. And then also, we also have the chi-square test. So the chi-square test actually allows us to be able to test for the independence or the relationship, to some extent. That's what other people talk about. And then also the differences between categorical variables. So if you take 2 categorical variables, maybe one is dependent variable, one is independent variable, could you say the differences in terms of the proportion between the 2 variables? And the answer is we don't know unless we perform a test like a chi-square test. So for a chi-square test, allow you to perform a test for when you have 2 categorical variables, right? So for a given 2 categorical variable, we are able to perform a chi-square test to assess. So again, with a chi-square test, the null hypothesis is that there is no differences between the 2 groups, or there is no relationship, or maybe there is no independent. It means that the 2 groups are, in other words, they are dependent. But then we have the alternate hypothesis, which is going to be the opposite of the null hypothesis. So now let us look at using our data set. We are going to test the quality of life. Now remember, the data set we are using is the Haynes data set, which is the 2020 Haynes data, which is the Human Information National Trend Survey data set, which was actually taken in 2020. So we are looking at the quality of life, which is when the person say the quality of care, sorry, the person say their quality of care is, let's say, poor, fair, very good, good, excellent. If the quality of care differ by gender. So the quality of care is a categorical variable, gender is also a categorical variable. So we are going to actually perform a chi-square test to be able to see whether there is any kind of relationship between these two variables, or maybe the quality of care differ by gender. So in order to test this, we use what is called, so again, within our data frame, so we are going to make a table. Now we always have to, before you can perform a chi-square test, we use what is called a contingency table. So you should be able to tell R to be R, for R to be able to develop this contingency table for you. And then now from the table, you can now move a step further to perform the chi-square test. So we assign our, we develop a new data frame of a table from our data, which is, so the DF is our original data. So within our original data, we call the quality of care, and then we also call the gender. And then we form a table from it, and then we go ahead and perform our chi-square test. And then we also have what is called the Fisher test, which is also the Fisher exact test, which is also pretty much the same as the chi-square test, which is also performing to actually know the differences between the categorical variable in terms of, their proportions. Okay, so now once you, so if we have to print out the table we formulated for quality of life and gender, so the quality of life, we have 4 levels of quality of life, which is, 5 levels of quality of life, and we have 2 levels of gender, which is male and female. So now we have been able to form our table. Now we say that we use the function chi-square dot test, right? So there's the function we use, and then we put into parentheses our table, the contingency table we formulated, and then now we print out. So once you print out, you are going to get this output, and then within the output, you are going to get your chi-square statistic, you are going to get the degree of freedom, and you are going to get the p-value. Again, a p-value, a higher p-value means we are failing to reject the null hypothesis, right? So it means there is no differences between male and female in terms of their quality of care, right? And then similar analysis which was performed for the Fisher exact test is also giving the same conclusion, right? Which means that male and female, which we have the p-value here, there is no differences in terms of the quality of life when it comes to, the quality of care. I keep on saying quality of life. Okay, so that's the chi-square test we actually have. So now, so there is the part 1. So now let us go to R, and then let's practically perform this analysis in R. Once we are done performing this analysis in R, we give ourselves about 5 minutes break, and then we can now come back to start performing some correlation and then regression analysis or modeling in R. So now let us switch to R. Okay. So now you have your, you have R here. If you have already opened your R, you have it here. And then now, first of all, you always have to be able to call in your data set, right? So again, DF, I'm assigning, and you can assign any name to your data, but I'm assigning my data frame, which I'm going to call the data as DF, right? So, and this is the line I'm going to run. So before even I run, if this is the first time you are actually being introduced to the R, this is the R interface. Okay, this is the R interface. So we have the source, we have the console, we have the environment, and then we have this the bottom right.
Sorry, Dr. Mamudu, we can't see the R on your screen.
Okay, thank you. I think, thank you for. Okay, now there you go. Yeah. Okay, so now, so if this is the first time you are actually being introduced to R, you are actually going to have this interface, that's RStudio. I actually prefer RStudio to R because it's very interactive. You are able to see everything as you go. So again, RStudio is built on R, just like I mentioned earlier. So you have the source. So the source is where you actually do all your coding, okay? And I will tell you the difference between the source and then the console. Now the source is when you type in if you do the coding under the source, right? The code stay there. Even if you close your R, or by default, let's say there was, let's say, power cut and your R closed automatically. If you reopen the R and you have not saved it, once you open it, you are still going to see all the code in the source. But if you code directly in the console, once you close R, everything is lost. So that's the difference between these two. So I would always want to code in the source and then run from the source so that I get the output in the console. And then you have the environment where whenever you assign any variable, it's actually any new assignment comes into the environment. So now the environment is empty. But as we start to call in our data set and others, we are going to see some information being populated in the environment. And then you have this part which we have the file, we have the plot, we have the packages. So you can see different R packages which are maybe already in your R. We have the help, we have the viewer, and then we have presentation. But most often what you are going to use most often is the plot. So that's basically the R Studio interface. So now let's go ahead and then do some analysis of what we saw on the slide, what was presented on the slide practical. So now we are coming to call our data. So we are assigning our data to DF, okay? And then we are going to read a CSV file. So we say read.csv, and then we have choose.file equal, and then we also want the header. Now choose.file will automatically will enter into your computer and open a window for you to be able to select your data. Okay, so I can put my cursor here and hit on run, and then it will run that line. So whenever there is a cursor, if I hit on run, it runs the line. But I can equally highlight the cursor, highlight on that particular code, and then also run it. And then I can also use Control Enter at the same time to run a particular code. So there are different ways of running. Okay, so now once you have run, you are going to see a pop-up. So this was the pop-up. So you would have to be able to locate your data. So now my data, the data we are going to use currently is going to be the hints data, which is of course, it has to be CSV file, which is this one. So I choose it. So once I have choose, you notice that when I call in this particular function of calling my data, there was some red sign here, which was actually telling you now there's a window which is open for you to actually get in your data set. Okay, so now once I have my data, I can, okay, maybe I want to look at the name of my data. So I put the cursor here, I can run. So these are the names of my data set. So I have the person ID, the HHID, we have the quality of care, insurance, age. So all these are. So how many? I have, I think, about 17 columns in my data set. But if you can see, maybe you would want to make a sense out of the data set by straight away performing some simple summary. So by performing some simple summary, you are able to see how your data set looks like, okay? So it gives you the descriptive, which include the minimum, the first quarter, the median, the mean, the third quarter, the maximum of each of the variables, right? And then what you should note is that once you perform the summary, if you haven't specified a variable is a categorical variable, R is going to think that it is a continuous variable. So it is going to give you a continuum descriptive of that particular variable, okay? Okay, so now you can now also, so what we are going to do next is I'm going to, now if you look at this particular data set, there are some unusual information we are seeing here, something like negative, right? The head age cannot be negative. So we have to remove the negative, right? I mean, the BMI level measurement, there's no negative BMI level measurement. So we have to remove them. So in the Haynes data set, -9 is representing like missing observation or missing value, or maybe an information which wasn't actually responded by the participants of the survey. Okay, so now I'm going to use this line of the code, and for each of the variables, so DF, so again, I'm going to still keep the same name, which will allow R to overwrite the first name. But I'm going to go into my data, the old data, which is this data set. And then I'm going to tell R that, okay, I need you to actually give me, so DF of quality of life. So for instance, if I say, just to give you an DF dollar quality of life. So DF, you see it has given me a drop menu. Now I can select a particular variable I would want to observe. So whenever you see a $sign, it's allowing you to assign a specific variable, or maybe choose a specific variable from your data set. So quality of life, I need everything to be greater than 0. The health insurance, the same. Age should be greater than 0. Gender should be greater than 0. So in other words, I'm removing all the minuses from the data set, okay? So now let me run it. So I have run this line of the code. So once I've run this line of the code, now I can perform the summary of DF again to see whether, so now once I perform the summary, you can see that now there's no negative for gender, age, there's no negative. So now I'm getting the actual descriptive for age, and the data is actually was conducted on adults in the United States, which means greater individuals who are age 18 years or above. So now I have the true age minimum, and then I have the maximum as well. And then the other variables which were also actually included, excluded. And now I have BMI. So the minimum BMI level within the data is 10. The maximum is 73.8. Okay. So now let us look at, so you can use N row to be able to know the number of observation within your data. So the number of observation, I have 2,490 participants within the data set. That's after cleaning it, okay? After cleaning the data set, there's what I was left with. But once you choose, you call in the data initially, you could have still used the N call to see the N row of the data frame to see how many participants am I having. And after you have excluded, to use the same N row to see how many people have I actually eliminated from the data. But for now, I have 2,490 people, which is a pretty good amount of data set. And then I would want to know how many columns of the data do I have. In other words, maybe the features or maybe the attributes of the data. So I have how many? 17 columns of the data set. And then remember, I told you, you can always use the name. You can use the name here. You can run the name to always look at the names you have within your data set. Okay, now let us go straight away and then perform the test, which was actually presented on our slide. So for instance, for one sample t-test, we actually look on the slide, we wanted to perform the test for BMI, right? So we can highlight on, so we say t.test. So t.test $ BMI means we are only focusing on BMI, right? So we can highlight on this and then run. But again, we can put the cursor on it and run, it's still going to run. Okay, so this was what we have. And then now we have the p-value, which is less than 0.05. So we say that we reject the null hypothesis, right? So by rejecting the null hypothesis, we say the mean BMI, the population mean of BMI is not equal to 0, right? So by default, if we are looking for the t-test of the BMI level, the default null hypothesis is 0. And then also, we can also perform the BMI for the t-test, and then we specify the confidence interval. So it is the same function, t-test function, but now we include additional argument, which is conf.level equal 0.90 or 0.90. So if I put the cursor there and run that line, again, I'm still getting the same thing, but now the confidence interval, which we have here, if you look at the output, the confidence interval we have here, it says 90% confidence interval. Whereas the initial one was what? 95% confidence interval. So there's how you can actually specify your confidence interval. And then you remember I told you you can use the $sign to actually learn more about a particular function. So assuming I want to learn more about t.test in R, I said question mark t.test, or the same as help into bracket in an inverted comma t.test. So let me put the cursor, let me run this line, which is the question mark t.test. Now I'm able to have, so if you come here and help, now you are able to see, view the documentation, and it explains every argument which is found within the t.test function. So X, what does X means? What does Y means? What does the alternate mean? What does the mu mean? You can read about it. And then you can actually apply it as you perform your analysis. And then again, if you look at the environment here, you can see the environment was initially empty, but now we have DF, which is the variable, the data frame we've actually we have currently, and then we are using it, we are performing an analysis on. So you can see now the data frame is being shown in the global environment here. Okay. So again, you can also perform t.test and then specify the null hypothesis. So if you don't want R to give you by default, the null hypothesis is equal to 0, and you say, no, wait. I have my own population parameter in my mind, and the population parameter by assumption is 20. So the population mean of the, let's say, of this particular data or US population is 20 for BMI. So you specify it, assuming you know it, and then you run it. So once you have run it, you see you have the output, and then again, the p-value is here. We reject the null hypothesis because the p-value is less than 0.05. Again, now we are saying that, okay, if you know the population parameter to be 20, then after the analysis, it says, excuse me, it's not 20. The population mean BMI level of United States is actually not 20, it's more than 20 perhaps. So it's different from 20. Hence, maybe we have to actually look for further investigation on this. Then also you have t.tests and then alternate. Again, you can specify the type of test you are actually performing here, okay? And then you can run it. And in the same t-test, you can actually specify, so this is calling the data for BMI, specifying the null hypothesis, specifying the type of test, and then specifying the confidence interval. You can do all of them in one code, right? And then we can run it, and then we see whether it's, so we can see that by specifying the mean BMI level is equal to 20, the alternate is less than, and then the confidence interval to be 90, we have the p-value is 1, which is just like, it's R is telling us what we have from the sample compared to what naturally maybe existed in the population is actually, we fail to reject the null hypothesis, right? So we say that the mean BMI is not, how do you call it? We fail to reject the null hypothesis. So by failing to reject the null hypothesis, we are saying that the mean BMI level is actually, is, let's say, approximately 20 as specified. Okay, so now you remember I told you can also specify the type of variance and then stuff and others which can be done. So we have the independent t-test. So the independent t-test, using the same t-test, we call our data set, and then we make a factor. So you would want to know the BMI level between gender, right? So again, we can say that BMI level for male and female. So we said by default, we are assuming is the mean BMI level of male and female equal. That's the null hypothesis. And that's what we fail to actually reject. And then that's what is telling us that yes, the mean BMI level may be the same for male and female. And then you can specify, if you have a very small sample size, you remember we talk about the homogeneity of the variance. So regarding the homogeneity of the variance, if you know the variance are equal, you can specify. If the variance are not equal, you can actually specify that the variances are not equal. And then you can actually go ahead and then run those lines. Okay, so next we also have, so this actually pretty much also the same thing. We are saying that we would want to actually see whether the mean moderate exercise differ by BMI. So what we did was we actually recategorized our BMI. So we said that we introduced a new variable in our data set. So the new variable we are introducing in the data set is BMI cut. So we say our data, go into our data and include a new variable BMI cut. So we bring the dollar sign. And then we use the function called the if else. So we said that if else, go into our data, choose BMI, and then for every BMI level less than or equals to 30, assign it 0. In other words, we call it not overweight. And then for any BMI level, so else you assign it 1, which is going to be overweight. So now we can run this line and then run our summary and see whether that has been added. So we can run the summary of our data. We can write a summary of the factor of the new variable which have been added into our data, which is BMI cut. So by running summary of the factor, we are telling out that again, it's a categorical variable and we want you to give a summary. So the true summary of a categorical variable for 0 and 1. So 0, we have 1651 individuals. For 1, we have 839 individuals. So now we said, okay, give us, we want you to test for whether the moderate exercise, for the mean moderate exercise for the 2 BMI, which is being either not overweight and overweight, is the same. So we perform this line of test, again, the t-test, and then we run it, and that's what we have. So we reject the null hypothesis, and the null hypothesis, which is the p-value is here, and then we are able to have the means, the how do you call it, the mean BMI for the 2 groups, and then we are able to know the confidence interval, but the p-value is less than 0.05, so we reject the null hypothesis, concluding that if you consider the mean moderate exercise for those who are overweight and those who are not overweight, they are different in terms of their moderate exercises. Okay, so we also had, you remember we had a per sample t-test. So we create our own artificial score for BMI level for 2 groups. So we call one of the groups score 1. And score 1 is representing the BMI level of people before they participated in a physical activity. And then score 2 is the BMI level of people after they have participated in a physical activity. And then we would want to know, are their BMI level the same? But before then, we are creating kind of a data or a vector for this particular, for score 1. So we run score 1, and then we can also run score 2. And then we can look at the mean, what is the mean of score 1? What is the mean of score 2, which is using these 2 lines. So now, given that we are looking at before and after kind of issue, we are going to use what is called the paired sample t-test. And to use the paired sample, you have to specify in R that we are using the paired, right? So we have specified that, okay, we would want you to perform the t-test for these 2 groups. to see whether they are the same using a pair sample, right? So you perform it, and then it says, so we failed to reject the null hypothesis given the p-value. So we said they are almost the same, right, for the score 1 and score 2. And then, of course, you can also specify the alternates as I've explained earlier within the t-test. Okay, so now let us move on to the ANOVA, which again, we have to first of all build our model, right? So we create the model, we are naming our model, or we are assigning our model to what? BMI ANOVA, so that's the model name. And then we are using the function. So now, anyway, maybe what I didn't mention is in R, the way you do assignment is to use less than and minus sign. So less than and minus sign represent assignment. So in other words, now I'm saying that I'm assigning BMI of ANOVA model. I'm creating a model, and then that model is going to represent the ANOVA of BMI for educational level, right? So that's it. So, and you can also use equal sign instead of the less than and minus sign. You can also use equal sign, and it's going to give you, so I can put the equal sign, and I can run this line, and I'm going to get. So now once I have run this line, I'm not able to see the output yet because I have to now call. So remember now, once you make any assignment, it displays in your environment. So now we have BMI ANOVA. So in the environment now, I can perform the summary of the. So by performing summary of the ANOVA, I'm now telling how to give me the results of the ANOVA model I've created. And there's the ANOVA model. Again, we have the p-value here. And then the p-value for the educational levels we have here, it is telling us that we reject the null hypothesis. So it tells us that the BMI, the mean BMI for the different educational level we have may be different, right? Then also, again, we can also create a table to see the mean BMI level for the levels of, how do you call it? For the levels of education, which is this. So by using model.tables of the model we created, which is BMI model. So we say model.table, which is the function, you put in BMI, and then we say we want you to give us the mean, and then we would want you to actually leave it in 3 decimal place, right? Yeah, so now this is what, or maybe we want you to leave it in just 3 digits, right? Yeah, so now there's what we have. So we have the mean BMI level of the different education level along with their number of observations. Then you remember I also spoke about the Tukis, right? Which allow you to perform the pairwise comparison of the groups. So by performing the Tukis of the ANOVA model, you are able to perform the pairwise comparison. And I already explained those p-values. And then again, to learn more about the Tukis function, the Tukey HSD, you just use the question mark and then you're able to see the function. Now let us look at the chi-square test. So again, for a chi-square test, you would want to test the chi-square of the quality of care and then the gender, whether there's a differences in terms of the quality of care by gender, right? So we create, first of all, we have to create a table. So we are naming our table DF tab 2, okay? And then we are saying the function we are going to use, we are assigning it, the function we are using is table, and we are creating a table for these 2 groups, which is quality of care and then gender. So now we can run that line. And once we run that line, it shows in our environment, right, as data that DF tab 2. It means a new assignment which has been created. So it is now there, and then we can now call our table. So by just running the table, we are able to see the tables, how the tables look like, which we have 5 levels of quality of care and 2 levels of gender. Then we can perform the chi-square test of this quality of care and gender, right? So we say the chi.test allows us to perform the chi-square test, which we have here, and then we are now able to also perform the Fisher exact test. Okay, so this is how you actually get the ANOVA, the R analysis for the three different aspects, which is either performing t-test, ANOVA, or a chi-square test. So now what I'm going to do is we will give ourselves, let's say, 5 minutes break, and then we come back, and then that's where we are going to start the regression and modeling part of this workshop. Okay, thank you very much. So we report back at, let's say, 11:17, which is from my end. Yeah, thank you. Okay, so welcome back again. from the 5 minutes break. Let me share my screen and oops. Okay, so let's share the slides. Okay, so just as I did earlier with part 1, we are also going to go through the correlation and regression analysis or modeling part of it through the slides, and then now we can go to R, actually finish up in R. Okay. All right, so we are looking at regression and correlation and regression. Usually when you talk about correlation, you are also talking about regression analysis, right? Yeah. So we are going to use this data, which is called the biomass data, which is the data set we are going to use. So again, you are going to be able to, I'm defining my data frame, which is, I'm going to call it DF bio, and then I'm going to assign it to the function, which is read.csv, and then now I'll be able to call my data set. Once I call my data set, I can see the names in the data sets, the columns names, the summary of the data set, how the data looks like, descriptives, and then also look at the, how they call the rows and then the columns as well. Okay. So, okay. So now when we talk about, correlation, you think about, we examine the linear relationship between two continuous variables. Of course, we will come to talk about correlation between categorical variables, but correlation in general, we are actually talking about a continuous variable, right? And thus we are able to compute the we are able to compute the statistics that allow us to be able to assess whether there is a difference between there is a relationship between that variable based on the magnitude we have. So we are using the biomass data set, and then we are going to examine the correlation between continuous variables. So within the biomass data set, we are going to now, after we have called in the data, we are going to use the function called the pairs. So the pairs function is actually going to, and then we are going to say pairs of our data, which is the DF bio. And now we are going to select some number of variables from the data. So we have the square bracket, comma, 5:8. 5:8 means give me the column 5 to column 8. So in other words, I'm just selecting 4 variables from my data set, right? So, and then with the pairs, it gives you the scatter plot of the 4 variables. Okay, so you're able to know. So the scatter plot in general is also allow you to be able to visualize the linear relationship between 2 continuous variables, right? So there's the scatter plot of the 2 variables within the biomass data. So these are the variables. So we have the rows and then the columns. So if you take LFBM, you are able to compare it. What is the relationship between LFBM and then LST, that's STBM, and then RTBM, and then LFNCC. So here we are able to compare LFBM with all the other variables to see their linear relationship. And then if we come to B, that's STBM, we are also able to compare the linear relationship with RTB. So if you look at here, row, by looking at the row, we are comparing the STB with RTB here, and then also with LFNCC variable, right? Now you can also have it in style, right? I mean, you can have a different visualization of the correlation of the scatter plots, which again, using, and that one, you can just use the plot function. So plot DF bio 5:8, which means calling the from 5th column to the 8th column of the data set. And then I have the PCH. The PCH allow us to be able to know that the size of the bubbles you are seeing in the scatter plot, right? The type of or the type you would want to see. And then also the size of it. If you want to see a bigger bubble, maybe you have to increase the CX, that the CEX, you have to increase it. If you want to see a much smaller bubbles, you have to reduce it. And then we have different colors. You can use blue, you can use, so I'm using still blue. Somebody can use red, and the colors is going to change to red. So that's just some visualization of the correlation matrix. Okay, using the same pair, in the pair function, we can still be able to, again, call our data, indicate the variables we would want to see their correlation, and then the PCH, which is, the type of bubbles we would want to see. And then we can say that call equal rainbow. So what we are doing here is now you can actually set R to be able to give you the correlation, the scatter plot, the scatter plot of two variables, and then also indicate the cluster within each scatter plot. So for instance, within the scatter plot, I want R to tell me the cluster of variables for N. So let's say N could be, let's say, gender, right? Let's say N could be, let's say, education. Let's say N could be some categorical variable, right? So I want you to show within the scatter plot the cluster of the categories within the scatter plots whilst comparing their relationship. And then I can ignore the lower panel. Now remember, if I go here, the lower panel and the upper panel, they are the same. So if you want to see it much clearly, you can ignore. So by setting lower dot panel to be equals to now, you are saying that, okay, I want you to exclude the lower panel, right? And I will exclude the lower panel, and then you are able to actually view the scatter plot by just seeing, and there's much easier to see when making those comparisons, right? Okay, so another way in which you can actually see the correlation. Now, all the while we are talking about the scatter plot, looking at the relationship, and within the scatter plot, we are still able to tell how to even give us the cluster of a specific population within the scatter plot, right? But we can also ask R to say that, okay, I would want you to give me a matrix, a correlation matrix of the variables, but then I would want you to give me the correlation coefficient, the distribution of each of the variable, and then also the scatter plot of each of the variables. So now, and you do that by using, first of all, if you have to install a package. So if you put in install.packages of psych, and then by using library of psych, you are activating or loading that package. So once you have done that, it means the package is ready. And within that package, we have the pairs.panels. And that is what allows us to be able to access the correlation matrix that gives us the correlation coefficients or the magnitude of the correlation between the variables, the distribution of each of the variables, and then the scatter plot of the scatter plot between the two variables. So we have the upper panel, which is the correlation coefficient. We have the lower panel, which is the scatter plot, and we have the middle panel, which is giving us the distribution of each of the plots. So now we can say that, or maybe, for instance, LFBM maybe is close to being normal. Maybe this is close to also be normal. We can say that RTB is quite right skewed. We can say LFNCC is kind of also close to normal. But then we can also see their correlation. So if you compare what is the correlation between LFBM and STBM, is 0.91, which is a very high correlation. And what you should know, correlation is usually measured between -1 and 1. One correlation, positive correlation start from the closer the correlation is to 1, the high positive correlation between the two variables. In other words, the linear relationship between the variables, right? And this is something you would want to observe prior to performing a regression analysis to see what is the behavior of the variables you are actually going to model or predict, along with even maybe the response you are considering. In other words, the dependent variable you may be considering. Okay, so now there is also even more plot you can actually use it to see whether the correlation coefficient is statistically significant or it's not statistically significant. So this particular plot here, which also you have to install a particular package, and then you have to load the package, and then you use the function called chat.correlation. So chat.correlation, and then you bring the data. So we are considering the F-bio of 4 variables, that's from 5th column to the 8th column. Now we are able to say that, okay, the correlation between LFBM and then STBM, which is 0.91, is statistically significant. Likewise, the correlation between LFBM and then RTBM is also statistically significant. And then the correlation between STBM and then RTBM, which is 0.58, is also statistically significant. And that is denoted by the stars we are seeing up there. So this is how you can also assess the test of the significance of the correlation. And it also, again, it gives you the insight about the behavior of the variable, because whilst we are going to perform some modeling, you are going to hear about what is called multicollinearity, which I will explain in our subsequent whilst we look at the model itself. Okay, so this is also another type of correlation in which you can actually perform. If you don't want any of those previous correlation, you can have a heat map of your correlation metrics of the 4 variables. So now you have to install dot packages of a particular package. You have to install the package. Library of that package means you are loading the package. And now we would have to create a variable, which we are going to call it core.mat. Okay, we are just creating it. We are creating a new variable called core, or function called core.mat. And then within that variable, we are assigning it to the correlation of this particular data, which is the bio of our 4 different variables. Then after you have created this particular correlation matrix, which is by assigning it to the core_mat, we now perform core plot. So the core plot, and then we use a method equal color. And then by printing out or running this line, we are able to see this kind of heat map. So what is the heat map showing? We are seeing the -1 to 1. So correlation is between -1 to 1. Now, the deeper the heat map of blue, the darker the blue, the highly positive correlated between the variables. So for instance, for a perfect correlation, which is you are matching the variable on its own by itself, it's very dark, which means it's a perfect correlation of 1. And it is the same for the middle. So the middle is matching the variable by itself. And when you perform a correlation of a variable by itself, of course, you get a perfect relationship. Then as the darkness reduces, again, the correlation continues to reduce. And then if you also look at, I don't know, I'm not very good at mentioning colors, but if you look at it, should I call it a pink close to dark red? So the darker the red becomes, it's also tell you the more it gets closer to become highly negatively correlated, right? Which we don't have many of them, because if you look at most of them, we don't have that very dark red. So that's how you can also create a heat map to be able to assess the correlation between your variables. So you can go row. So by going row, you are able to match the variables by variable and then perform the correlation. Okay, so now let us also look at, now we have to test for correlation, right? You perform a correlation test. To be able to test for a correlation is pretty straightforward. You use the function call, and then you call, so you can perform the correlation test between two variables, continuous variables, of course. And by performing before, then you would want to obtain, let's say, the correlation of that variable. So we can, to get the correlation coefficient of a variable, we can just use call, we call the variable, so we have the FBio $ of that variable versus the FBio $ of that variable. And that will give it the correlation coefficient. But then if you want to perform the test, the correlation test gives us a null hypothesis, which says that no correlation or no linear relationship between the variables. Okay, so by putting in call.test function of the two variables, you are able to print out their correlation test. And then when the correlation test, again, a less than 0.05, we say we reject the null hypothesis. And by rejecting the null hypothesis, we say there's a linear relationship between the two variables. In other words, there's some form of correlation between them, right? And then you can have the confidence interval. Again, the confidence interval includes 0, then of course they are not statistically significant. And then this is the magnitude of the correlation between LFBM and then STBM. Okay. Now, great, we've been able to assess the correlation among the variables, right? At least we are able to have a fair idea on our mind, maybe variables that may be correlated, and to see before we proceed with our modeling, right? So now we are now coming to look at the regression model. So in a regression model, it's a statistical model that estimates the linear relationship between scalar response and then also one or more explanatory variable, which is called, so the scalar response is called the dependent variable, and then the explanatory variable, we call it the independent variable. So when you hear explanatory variable, it's the same as independent variable. And then when you hear a response variable, we are still talking about dependent variable. Okay, so simply put, a linear regression actually allows us to be able to predict the value of a particular variable based on another variable. Okay, so we are doing some form of prediction. So in other words, let's say if you give me a person, if I want to predict, let's say BMI, I would say if you give me a person age, maybe I can use age to predict the person BMI, right? So this is how linear regression actually envisions. And then also the variable you want to predict is called the dependent variable. And again, the other variables are called the independent variables. But then in using linear regression, there are some assumptions that have to be satisfied before you end up by saying that, oh, I have a very good model, and perhaps the model is also giving me some kind of a good accuracy in terms of the maybe percentage explanatory between the dependent variable and the independent variable. So some of the assumptions is the linearity assumption, and we are going to handle these assumptions one by one as we move forward. So we have the linearity assumption, we have the multivariate normal. So the linearity assumption says there should be a linear relationship between the dependent and the independent variable. And how do you assess that? We already did that using correlation, right? We were able to, using the scatter plot we built earlier, to be able to assess whether there's a linear relationship between these two variables. And then there should also be multivariate normality. So in other words, the errors or the residuals within the model have to follow normal distribution. And then we also have what is called the homoscedasticity. In other words, the errors or the residuals must have constant variance. So when you hear homoscedasticity, it tells you constant variance or variability in our errors. And then also no multicollinearity. So multicollinearity, which again, this I will explain further. Multicollinearity measures the correlation between the independent variable you have in your data. So if you are modeling, let's say, BMI level and several other independent variables, like let's say age, physical activity, let's say the education of the person. If you take all those independent variables, the age, the physical activity, the education of the person, are they correlated? And it's important to actually look into this, because sometimes a very highly correlated independent variables can actually lead to overfitting. So in other words, it will end up you maybe predicting and end up coming up with a wrong prediction, right? Maybe overestimating the prediction you are actually giving, right? So it's important to actually take note of that. And more importantly, in our human life, so many attributes can be very correlated, even particularly if you are into the economic field or the finance field, where, for instance, one variable is used in measuring another variable. For instance, let's say if you want to measure the gross domestic product of a particular country, the GDP, you might want to have, let's say, maybe the consumption, let's say the inflationary factors, let's say the employment factors. There are several other factors you might want to consider, right? And these factors are used in calculating GDP. So in other words, if you are actually going to measure, you are trying to predict a particular phenomenon which has GDP and all these other factors in the same model as independent variable, then of course, you are likely to observe some form of huge correlation between those variables, which has to be taken closer look at. And then also we have what is called there should be no autocorrelation. So in other words, your errors has to be independent and then has to be uncorrelated. Okay, so when it comes to simple linear regression in your mind can say, let's say, a bivariate regression, okay? In other words, you are looking at one response and one independent variable, which is a simple linear regression. And there's the regression function, which in a regression function, we have the response, which is the dependent variable, the constant term, we have the independent variable with its coefficient or parameter, beta, and then we have the error. So this error here term takes into account any other information that is not included in your statistical model. Okay. Yeah, so now you move on. So we actually have a bivariate regression model. So in R, the R documentation for regression is LM. And again, you can read more about the argument within the documentation by just using the the question mark of LM, and then you'll be able to learn more about the arguments within the LM functions. So now what we are going to do now is we are going to use the biomass data, and then we are going to actually use, how do you call it? Use STBM to predict LFBM. So in other words, the STBM become our independent variable because it is what is going to predict LFBM. So LFBM become our dependent variable. So now we build the model by saying model bio LFBM LM. So now we call the response variable, which comes first, which is the LFBM, which is the dependent variable. Then we regress it. So we use this small, how do you call it? I think the approximate sign as a regression sign to equate it to the independent variable. So we have the STBM. And then now we call in our data set. Our data we are using is the DF bio data set. So once we have developed, so this is a simple regression model of just the dependent variable and then one independent variable. So a summary of it will give us the output, okay? And then now we also have, using the Haynes data sets, another person can also, let's say I want to see whether the moderate physical activity predicts a person's BMI, okay? So I said, I develop a model BMI, I assign that model to the LM function, I call in my BMI, the moderate physical activity, which is my independent variable, and then the data, which is the DF, which represent the hints data. And then I print out by using summary of the model. Okay. So now let us look at if assuming, and then also we have, so now I just move on to the multiple regression, okay? Because in a real life, you may not have maybe a bivariate regression, because there are several phenomena which can influence an outcome, right? So if you take, let's say, even if you are thinking about the BMI level of an individual and you are thinking about whether physical activity influence BMI level or maybe predict BMI. So aside physical activity, what about the age of the person, right? Maybe people who is very aged, let's say 80 years, may not be involved in some huge physical activity, right? Maybe what about the sex of the individual? So there are other factors. So in a real life, you are not going to have something like a one-on-one regression, but usually you just want to know, you can also use it to measure the linear relationship between the dependent and independent variable. Okay, so now let's look at the multiple regression. So in a multiple regression, we have, again, you are going to have one dependent variable, which is a continuous variable. And then you are going to have an independent variable, which, of course, the independent variable can be either continuous or it can be, how do you call it? It can be categorical variable or nominal variable. So again, we are building a new model, which is model 2 of bio of LFBM. And then we are going to use the LM function. And now we are going to use the plus sign to add more variables to our model. So if you look at the initial model was ST, the independent variable was only STBM, but now we are adding another variable, which is the RTBM. And then now we call our data set. So now we print out the results. So by printing out the results, you can see here that the results is going to give you, so this is the regression table you are going to see after printing out the results. You are going to be able to see the independent variables. You are going to see the constant term, and then you are going to see the estimate, in other words, the parameters of the regression, okay? And then you are also going to see the p-values, which is measuring whether the independent variables prediction of the outcome or the dependent variable is significant, right? So now these are the estimates. So assuming we are to use this estimate to draw this regression line, we are going to have this alpha here to be 0.09, and then we have beta 1 to be 2.28, and then we have beta 2 to be what? 0.012, right? But then let us look at the statistical significance of the independent variable. STBM is statistically significant because the p-value is less than 0.05. So we say statistically significant. So we reject the null hypothesis and say that, okay, the STBM indeed have some influence on predicting, how do you call it, the outcome, which is the LFBM. But other statistic in which you can actually look out for in your regression model is the R squared. Okay, so you are going to see an R squared, and then you are going to see the adjusted R squared. So the R squared and adjusted R squared, it gives the same explanation, right? Yeah. So with the R squared, both of them is telling us how much the independent variables we have in our data explains the dependent variable. So in other words, how much does STBM and RTBM explains LFBM? And then in percentage-wise, we can say that 83.1% variation in our response, which is the LF or the dependent variable, which is the LFBM, is being explained by the independent variables we have here, which is the STBM and then RTBM. Right? But again, what you should know is that the RTBM is not statistically significant. And that's something, whilst you perform the model, is something you might want to actually look at, whether maybe certain factors may be influencing it from being significant or in that manner. Okay, and then also, so this is actually a very good kind of given the high R square and adjusted R square, which is very close, it's a very good model. And another thing you might also want to look at is the standard error, the residual standard error, which is very small. If you have a very small residual standard error, the better for your model. Okay. Okay, so now let us now given the model we have built. So we are going to use this particular model, okay? But again, those of you can perform your own model using the Hines data to find whether moderate exercises and age predicts BMI level, okay? But we are going to stick with this model and then use it to actually develop and then assess our, how do you call it? Our assumptions. So here are the model assumptions. So first of all, when you think about, now we are looking into the model diagnostics, okay? When you look at the model diagnostics, it's basically telling you you are examining the regression model and assumption and other factors. Just like if you go to the doctor, before the doctor may diagnose you with a particular disease, the doctor may want to look at several factors which particularly could actually result in diagnosing you with that disease. So when we talk about model diagnostic, we are again looking at the factors which have to actually exist to be able to say, oh, you are actually having this particular disease, okay? So now we have assessing the linearity of the model. So to assess the linearity of the model, you can actually, once you have built the model, so now in this model, we are actually using, given that this particular variable was not significant, which is RTBM, okay? I decided to drop it out of the data, okay? And then we are only focusing on this one, STBM, to see how much the STBM predicts the LBM independent variable, okay? Dependent variable. So now we are only focusing on whether STBM predicts the LFBM, okay? So we develop our regression and then we actually find the summary. So once you print out the summary, you are able to see. Oh, oops, okay. So now let's go so to find the linear relationship between LFBM and then STBM, you can just use, how do you call it? You can use plot. I think there's something I excluded here. You can use the plot of the model, and then you actually use the AB line to actually draw the regression line to see how much the independent variable is actually influencing our dependent variable. But then there are also, and to observe the linearity, there are other packages which allow you to actually observe the linearity and give you something which is called like the partial plot, right? So you are able to install this package. So you install packages, you load that package by using the library function. And I would also want you to install this particular package and then also load that particular package. And then by using CR plots of our model, which is this particular model, we are able to see this plot. Now we are seeing a plot with the original blue line, which is the blue line which was observed in the top panel. And then we are seeing the pink line. So the linear and close the blue line is to the pink line. We assume that the linearity assumptions is being satisfied here, okay? Now there are other assumptions, which is the normality assumption, which we said the errors should follow normal distribution or should be normally distributed. Now the way in which you assess the distribution of this particular variable is actually using what is called the QQ norm of the residual of our model. Now again, our model in which we built was this particular model, right? So the residual, so finding the QQ norm, which is the function into bracket, the residual of the model, means we want to know the normal, we are trying to assess the normal distribution of the model, right? And then we also have the QQ line. The QQ line is going to draw the line through the points, okay? Now, the further away the points from the line, the more likely we are going to say that our model or our residuals are not normally distributed, okay? But the closer, or if the line is able to draw through all the points, then you are more likely to have a normally distributed residuals. And that means your multivariate normality assumption could be satisfied. So, okay, so another package to see in which you can actually draw a different KQ plot is by installing the CAR package and librarying the CAR package. And in that package, we are going to have what is called, once you have loaded it, we are going to have what is called the KQ plot of the residual of our model. And then now we are going to have we are going to name our x-axis as the theoretical quantiles. And then we are going to label our y-axis as the sample quantiles, right? Which is just like when we use the KQ norm, what it gave us. But this time we are manually trying to figure it out. But the interesting thing, the interesting part of this particular KQ plot function allow us to be able to also draw a confidence interval, okay, to see whether our residuals fall within a confidence interval. And if if all the residuals fall within the confidence interval, is also a likely that that assumption of normality is satisfied, right? But it also gives us a clue of some observations that may be going out of bounds, or maybe that may be causing some form of problem in our model, right? So for instance, it is indicating observation 23, observation 24 within the data set. Maybe we cannot conclude yet, but there could be an outlier within the model, right? Or maybe some influential observation, which we might want to look much into those kind of observation to see whether maybe if we take them out, how much does that impact the model? If we leave them in, how much does that impact the model? Those are things we have to look at. So, and then now we have a formal test of a formal test. So with a formal test, we can test a formal test using what is called a Shapiro-Wilks test, which we have Shapiro.test, which is of the residual of our model. And if it is testing using the hypothesis, the null hypothesis that the residuals are normally distributed, okay? So now, if we reject the null hypothesis, then it tells us that the residuals are not normally distributed. And the p-value here of the Wilks test is what? It's very small p-value, which means we reject the null hypothesis. So even though in our visualization, we can see more of the points are within the confidence interval, only few of the points are out of the confidence interval, but yet they are actually impacting the normal distribution of the model, which means we may have a good model which is giving us a prediction of about over 80% R square, but that doesn't necessarily mean it's a good model because the assumptions have still not been satisfied, right? So it's a call for concern, and as a model builder, that's something you have to look more into it to be able to achieve a p-value, which is a high p-value enough to be able to fail to reject the null hypothesis and then conclude that your residuals are normally distributed. Okay, so another assumption we are looking at over here is also the homozygosity assumption, okay, which we said we need our errors to have constant variance, right? Again, there should have to be some variability within our among our errors, right? So we can plot, we can just plot to see the residuals and just observe it and see whether they are, there's a possibility of they having a constant variance. So the way you do it to use plots, then we have the fitted of the model. So once our model, so we have the fitted of the model and then the residual of the model. So once we plot the fitted and the residual of the model, and we have the AB line of 0, 0, which is a blue line here. Now, if most of the points are randomly scattered in the plot around the AB line, then perhaps we are close to achieving constant variance, which of course, by looking at this plot, you can say, maybe. But then again, it's also giving us a clue of some possible observation, which may be an outlier, which can be some concern to look into, right? Then also, we have a formal test for, how do you call it? We have a formal test for the constant variance, which you have to install this package. Again, you might have already installed it, so you don't have to reinstall it if you installed it previously. And that function is called the NCV test. So the NCV test of the model actually allow us to test for the homoscedasticity to see. Okay, so, and then we are actually going to look into that once we go to okay, so now we also have, how do you call it? We also have your, sorry. Okay. So you also have other things to also assess for, which we have the assessing the multicollinearity. And the multicollinearity, we have a function which we can use to assess the multicollinearity, which is the VIF function, right? So when the VIF function is usually less than or equals to 10, then we said the independent variables are not correlated, okay? And then you can also assess for the autocorrelation, okay? So we have this function called the VIF function of the model, and that actually allows us to be able to assess the multicollinearity. And then before you assess the before you assess a multicollinearity, then of course you should have more than one independent variable, okay? Because the VIF is actually going to compare the independent variable to see whether they are correlated, okay? So that's why in the VIF, this is the model we are going to use to be able to see whether these two variables we have in the model are highly correlated. If they are highly correlated as a model builder, there's something you have to actually look into to see how sometimes some recommendation have been, if variables are very highly correlated, maybe the possible option will be for you to actually throw one of the variable out of the model. I think we might go a little bit beyond our time, so just forgive us. And then we are close to wrapping up very soon and looking at the aspect of it. Then we also have assessing the autocorrelation, which we have a test which is called a Darwin-Watson test. The Darwin-Watson test is also a formal test that is going to actually allow us to be able to assess the multicollinearity, to actually see whether our errors are correlated. Okay, so then we can also assess for outliers within the model, okay? So in the model, we can assess for outliers. So by using outlier tests of the model, we are able to see, assess a particular format test to see whether, to see those possible observations that are actually outliers in the model, okay? And then also we have the influential observation, which now somebody may ask, what is the difference between an outlier and an influential observation? Now the difference can be pretty, can be similar, but to the extent can be different. Now, an influential observation is not necessarily an outlier. So whereas an influential observation may not be an outlier may possibly be an influential observation. So an influential observation is an observation which may have an impact in your model, right? The accuracy of the model, let's say the R-square of the model. Those are influential observations. And you actually assess that using the influence measures of the model, which is the function that is being used. And then by printing out the summary, you are able to get all the observations that are possibly influencing our model. And those observations, as a modeler, you now decide, okay, maybe should I take those observations to see how much my model behaves, or should I leave those observations in the model? So that's something to look into. Okay, so the final part of the linear regression aspect, which is the logistic multiple linear regression, logistic linear regression, is you can also print out the residual analysis to assess the influential observation. And that is by just using this function. So if you have the model, we actually use the function plot of the model. By using the plot of the model, we are able to see these different plots, which is 4 different plots. And for each of them, we are able to know, for instance, we are seeing observation 24, 23, 54 are all likely observations that may be influencing our model, which we may look at. So you are seeing the residual versus the fitted model. You are seeing the QQ plot, which we earlier on saw. And then you are seeing this one is looking at the standardized residuals versus the fitted. And then this is looking at actually the standardized residual versus the leverage, which gives you the Cook distance. How distance are some of the observation apart from the model, right? So now, finally, before we go to R, let us look at the last aspect of the regression, which is going to be the logistic regression, okay? Now, logistic regression, which is something which is being used in, how do you call it, in health analysis or analysis of a categorical variable. Remember, I told you you can have, you will be able to assess the relationship between a continuous variable. If you have a continuous response, then linear regression, which is the multiple linear regression, also will be the option. But if you have a categorical response, then linear regression is not an option for you. Then possibly you will be thinking about using the logistic regression, okay? And logistic regression can have several, there are several different logistic regression you might have, which we have the binary logistic regression, which means your dependent variable have only 2 outcomes. For instance, let's say either obesity or not obese. Then you have multinomial logistic regression, which means your dependent variable have more than 1 outcome. And then you have the ordinal logistic regression, right? Which means your dependent variable has more than 2 outcomes. So it has 3 or more outcomes, but those outcomes are ordered. So maybe you are thinking about, let's say, predicting the grading of maybe students, right, from A, B, C, D, right, which is something which is ordered. Then you are thinking about an ordinal logistic regression. But we will not go into all those ordinal logistic regression. We will not go into multinomial logistic regression. All what we are going to look at most is we are looking at the logistic, binary logistic regression, which we, in our documentation or command, we are going to use the function called the GLM, okay? So this is a GLM function. And again, in R, you'll be able to assess the meaning of this argument just by using question mark of GLM. Okay, so once you have performed your logistic regression, for instance, we want to perform, we are going back to using our hints data set. And in the hints data set, we are going to recategorize BMI into obese and not obese. So let's say those who are 0 are not obese and those who are 1 are obese, okay? So 0 means they have BMI level less than or equals to 30, and 1 means they have BMI level greater than 30, okay? And then we are now going to have to summary. So we can just see the summary of that new variable. So now here is where you have the logistic regression. So we are going to have the logistic regression, which we are going to give it, assign it a name, log model of BMI. So we are looking at BMI by measuring obesity of the individual, right? So we have BMI cut, which is the response variable, which have 2 outcomes, which is 0 and 1. 0 means not obese, 1 means obese. And then we are regressing it on these factors. We are regressing it on age, gender, education, health insurance, okay? But then for each of these variables, they are categorical variables. Hence, we have to tell R that, please, these variables are categorical variables. Hence, within the model, within the GLM function, we are going to have a factor of age group. And then if a factor of age group, what then become your reference group, okay? Because we would want to be able to identify the reference group. Now, logistic regression gives you an output of the odd ratios, right? And these odd ratios, the way you interpret the odd ratios is being able to compare each of the variables with a reference group. Okay, so for age group, you want the reference to be 1. For gender, we want the reference to be 1. For education, we want the reference to be 4. And then for health insurance, we want the reference to be 2, right? Okay. And then now we want you to give us a regression. And then the family of regression in which we are going to have is the binomial regression, which gives us the logic function which perform the binary logistic regression, okay? And then we print out the summary of the model. So when you print out a summary of the model, some of the key information you can see, you are able to observe the estimates of the model, which is the coefficient, okay, estimated coefficient of the model, which in other words, if you go here, the beta naught, beta 1, beta up to beta k, right? And beta naught actually represents the constant, and then beta 1 to beta k represent the other. I think I should have bring dot here. Yeah. Anyways, so then we also have the p-value, which allow us to be able to know are the categories we are observing statistically significant? Are they influencing? Are they associated with our dependent variable, right? So in other words, if you take the different age levels, right? If you compare age level, the age group level 1 was the reference group. So if you compare reference group 2 to the reference group, is this statistically significantly different in terms of how much they influences our dependent variable, which is obesity? So that's it. And then also, you also have, here is where you are able to actually observe the logistic, the odd ratio itself, which in other words, it could also be called adjusted odd ratio, given that you are having several other risk factors within the model. Okay, so you have the odd ratio here, and then you have the confidence interval. Now, when the odd ratio include 1, then it means it's not statistically significant. If the odd ratio does not include 1, then it means it's statistically significant, okay? Just as you are, and you can actually look at it based on also comparing it to the p-value. So the odd ratio of less than 1, an odd ratio of less than 1 tells us that there is an decreased odd of obesity for that particular variable. So for instance, age group 2 has an odd ratio of greater than 1, which means they have an increased odd of obesity compared to group 1. The same thing, age group 3 has an increased odd of obesity compared to group 1, group 4 the same. But then if you come to insurance, people who are without insurance have, people who have insurance, I guess, I don't know, I have to check. 1, maybe, I think people who have insurance or without insurance, but either way, the insurance group 1 have decreased likelihood of obesity or odds of obesity compared to the insurance group 2, which is our reference. Okay, so quickly, which would take us longer of a time, let us look at the R, how quickly we can actually do this in R, which shouldn't take us much of a time before. Okay, so now in R, you can actually perform these functions in R. So basically, I've explained all of them. So what I'm going to do is I'm just going to run them for you to see. So now we are calling our data, which is the bio data, okay? So we call our data, then we choose the data. So we are going to use the bio data, okay? So now we have run it. So now it's active, okay? So now we can we can know the names in the data, summary of the data, the number of observation within the data, and then the number of features or maybe the number of columns within the data set, okay? So, and then also we can, a summary of the n of factor means this n is a categorical variable, right? So now plot of, so choosing this column 5 to column 8, we would want to plot this function using the pairs. So by using the pairs, we have the output. And then again, by using plot and then specifying the color, you are going to also have a different output, right? And then we can also specify, now given that this n, remember this n, is a categorical variable of 1, 2, 3. So we would want within our correlation, we would want to see the cluster of those points of our endpoints. So give us those points within the scatter plot, okay? And then we are going to use rainbow of 3 colors, okay? So we can do this, and then now we have it here. And then I have already installed and then activated my psych. So now I can go ahead and use the panel, the pairs.panel, okay? And then there's what I have, which I've already explained this plots. And then I can also, how do you call it? Once you have installed this and then you have loaded it or activated it, you can use the chat.log correlation of those variables to also be able to observe a correlation metrics of the magnitude, the significance, the distribution of those variables. Then also by installing this particular function and then loading it or activating it, now you create a correlation matrix of the 4 variables. So now I created the correlation matrix. And now I'm going to have a core plot of the correlation matrix, okay? And then the method is I need some color, and that is going to give me the heat map. So I have the heat map. And then now the correlation test, I can find the correlation coefficient between 2 of the variables. So if I want to see the correlation coefficient between LFBM and then STBM, okay, I can now run it. And then now it's 0.911, which we saw earlier. And then I can run the correlation test to be able to see, okay? Yeah, so with the correlation test we have over here, which means p-value, so we reject the null hypothesis, right? So by rejecting the null hypothesis, it's telling us that there's a correlation between the 2 variables, right? Which is the LFBM and then the STBM. So now with the regression model, again, this simple linear regression of LFBM and then as my dependent variable and then the STBM as my independent variable. And I include the data. So the LM function, my dependent variable, my independent variable, and then the data, which is a simple linear regression. So which I have loaded it. So I can now use the summary to see the output, which I have already explained this output. And then also you can also have a multiple linear regression. So again, you can also model how do you call BMI on physical activity on BMI and then see whether the output. So with a multiple linear regression of LFBM, I'm going to also consider 2 variables, which is as my independent variable, and then also giving the data set, right, in the LM function. So now this is the new name I'm giving this multiple regression, which is the model 2 bio LFBM. You can name it whichever way you want. So now when I run it, I'm able to get the regression output for this, okay? And then also one thing you also always have to be look out for is whenever you perform a regression output, you have to make sure your constant term is statistically significant, okay? This constant term is showing a borderline significant, but if it's not significant, then it means there's it raises question about how much the linear relation between your dependent variable and then your independent variable, okay? Then also, you can also plot these functions, which I did earlier, to be able to see how and this is actually given the regression line of the dependent variable, and then so you can go back to see the plot by using this arrows. So this is the regression line. And then now the model diagnostics. So you can actually use a plot of LFBM with this, which actually gives us again, it gives us, so if you don't want to go with what is up here, you can use the plot of LSBM, and then you are able to get the plot. And then AB line, actually draw line through to able to see the regression line. And then also by using, we can test for the linearity, okay? By installing this package and loading it, we can test for the linearity. And then again, the closer the pink line, the better you can say there is a linear relationship. There is linearity assumption is satisfied. And then you can also, the core of these two variables is you can actually use the core to find it. And then also now we can also use QQ norm of our model, QQ norm receipt of our model to be able to find the QQ plot. And then QQ line is also going to allow us to draw a line through our QQ plot. And then now we can have, if you have loaded this particular package, you can use the QQ plot, and then with all this information, the X label, which means the label of our X, the Y label, and then others. And then the main is the title, okay? So by running it, you can be able to see this particular function. And you can zoom it. We can zoom to actually see it, okay? You can zoom to actually see it using from here. And then we have also homoscedasticity. We would want to see the residual plot, okay, of the fitted, and then the residuals of our model. So the fitness of the model and the residual of the model. And then we draw the AB line of 0 through 8 to see how much the residuals are actually populated around the 0 line. And then also we can perform a formal test, okay, to test whether there is a constant variance, okay? And that is the NCV test, okay? And then the NCV test, okay, we reject the null hypothesis. So the NCV test the null hypothesis, right? Of if you reject the null hypothesis, it means there is no constant variance. So the null hypothesis tells us that there is constant variance. So by rejecting the null hypothesis, it says there's no constant variance. So which means we have to further look into what observations that may be actually causing problem of lack of constant variance or homoscedasticity. Then now we can also have the VIF of the model. Now the multiple regression model, which have two independent variables, we can have the VIF to assess them and see. So the VIF of each of the variables is 1.5, 1.5, which is less than 10, right? So it means we don't have issue of multicollinearity between the independent variable. So remember the independent variable of our model was these two variables, right? So, and then we can also perform the diagnostic test to test whether the errors are correlated. And then also by testing the diagnostic test, the alternate hypothesis says that the errors are not equals to 0. And then we have the p-value, the errors are equals to 0. So, okay, so by failing to reject the null hypothesis, we are saying that, I mean, the errors are what are correlated. The errors are correlated, okay? So now we have the outliers, which we can perform an outlier test, which I said, to see which variables are actually causing the problem within our model or observation. So now, constantly, if you can remember, if you go backwards to our, oh, I think that plot is not here. Okay. But then if we go, I think backwards, constantly we were having this particular observation. There was one particular, okay, observation 24, which seems like an outlier. And then the outlier test is going to actually let you know whether this particular variable is an influential variable, right? And then failing to reject the null hypothesis tells us that this particular variable is an kind of an outlying variable which have to be looked into, okay? And then also we have the influential observation. So if you put the influential measures of the model we build, we are able to see we have 54 observations. So for all the 54 observations, we are able to assess all the influential observations. And these are all influential measures, which if you go deep into statistics, you come to understand the meaning of these influential measures. But however, we can perform a summary of the influential observations to see in summary which observations are likely to be an influential observation, and maybe to consider whether these observation has to again to be taken out one by one from the model to see how much the model improved or maybe did not improve. And then again, as a model builder, that is something you have to do. And then also we have finally, and then you have this particular function here, okay? Before that function, let me print out plot of our model will give us the residual of the, so the plot of our model, once you have run this particular line, plot of the model, now you have to come down here, put your cursor, and then hit enter. Now you are able to see the different residual plots, 4 different residual plots, okay? But then you can actually put all the 4 different residual plots into one plot, which you saw it in the slides, okay? So that is par mfro equal 2 rows and 2 columns. So this one, I'm telling R that I want you to give me a plot of 2 rows, 2 columns, okay? So here is it, so 2 by 2. So now I can print out the plot again, and now I'm able to observe all of them. I can open it and then see all of them. I'm able to assess the residual. Again, 24, 54, 23, these are observations that have to be critically looked at. So, and then finally, regarding logistic regression, which we are almost done here. So in the logistic regression, we are going to actually model BMI, those who are obese and those who are not obese, right? And then we are assessing whether these factors influences individuals who are obese. And remember, obese was actually was 1 in our categories, right? Okay, so now by using the DLM function, we've factor of our, of our BMI cards, which give us the 2 factor of whether obese and not obese. And then now we put in all the other functions. We make sure we assign the reference, and that once we can highlight on all of them, or we can just run that line. And then once we have run that line, we can print out the results. Now, what you should know is if you don't put in the factor, okay, I would think they are continuous variables. Hence, you are not going to get these different comparisons after your output. That's why it is important to include the factor within and then also assign the reference. So finally, we can use the coefficient of the model to see the coefficient, all the coefficients of the model, which of course is fine here, which is the same as here separately. And then also the confidence interval of the coefficients, we can also see the confidence interval separately, which of course, we can see the confidence interval separately. But more importantly, which is something which is actually needed for our interpretation of the model, is the estimator of the odd ratio, right? So you use the exponent of the coefficient of the model to print out your odd ratios. So by so doing now, we have the odd ratio of the intercept. We have the odd ratio of group 2 of age. And for each of this odd ratio, we interpret it by comparing it with the reference group. And finally, we can print out both the odd ratio and that of the, the confidence interval together, which we use the exponent of this. And then now we can print it out. So now we have both the odd ratio and the confidence interval print out. And again, when your confidence interval include 1, it means there's no statistical significance for your odd ratio. And then we also have the ANOVA of the model, which actually gives you some table of deviance of that actually of the model, and then you are able to assess the deviance of the model. So now last thing I would want to show everyone. So oops, let me share this. Okay, that's a my screen too. Okay. Are you able to see my screen too? My screen?
No, we cannot.
Oh, okay. Oops. Okay, so finally, so this is the introduction which actually I wanted to give you regarding statistical inference, and then when it comes to you actually performing some kind of modeling, right? So this is just to give you some kind of foundation. You may be good in R, you may not be good in R, but there is something which gives you an idea of how to, a starting point at least. And if you're already good in R, at least you still have some additional tool which is going to boost your skill set in R. So finally, we will appreciate it if you actually leave some form of evaluation. If you have any question, I would have loved to actually answer several questions from our audience. But if you have any question, you can send it to my email. I'll be more than happy to answer you through an email. And then if you answer this evaluation, it's able to tell us, to allow us to know what type of workshop would you need, would you want us to have for data analysis in the future, right? Which is very important. And again, as a means of actually helping people who may or may not have even the money to attend a workshop, a paid workshop. Now we bring it to you for free through the collaboration of ESG and the Department of Public Health at Cal State Fullerton. Okay, all right, so thanks to everyone. Thank you very much. I really appreciate you stopping by. And then this particular workshop was made live on Facebook. So you can actually search for me on Facebook if you want to actually review it as well. You can actually review it as many times as possible because it's on my Facebook page. And then it is also recorded, and yeah, and it will also be made perhaps available through YouTube. Okay, so thanks to everyone. And then maybe I'll leave maybe just 5 minutes. If anybody have some specific question you want to stop by and ask that question, you can show your face. That's fine. If you wouldn't mind, you can just show your face and say hi. But if you have a specific question, we can just have maybe 5 minutes and talk about that specific question, and then we bring the entire meeting to an end. Thank you, thank you, thank you. Again, please try to submit the evaluation of the workshop, and then that will be very helpful. Thank you very much. Let me see the chat. Was there any thing in the chat? Any question in the chat? Oh, you know, there was one thing I actually forget. Anyway, that's fine. We could have asked the audience to actually put in maybe their kind of profession and where they are coming from, right? Just to be able to know the kind of audience we have. But that's okay, maybe in the future. But if we're still here, you can just maybe put in where you are joining us from in this workshop. So someone said, I mean, I'll make the recording available maybe at the end of next week, it should be available, or maybe even I can make it available on YouTube tomorrow. Yeah, so you can actually go on YouTube and you can actually, if you search for me on YouTube, maybe you should be able to see it as well. Okay, thank you. Okay, so I think we still have some guests. Do they have some question for us? Oh, I have my brother and friend joining. My brother and friend joining here. Rasmus. Okay, so I think maybe we can just okay, so I